Binding energy and mass defect. The total mass of the nucleus is always less than the sum of its constituent neutrons and protons. But where has all this mass gone? It's become energy. It's either radiation, which means emitted particles, or gamma rays, or it's kinetic energy. The difference between the total mass of the nucleons and the mass of the nucleus itself is called the binding energy of the nucleus. In energy units, the binding energy is determined by E sub B equals the change in mass, the mass deficit, times c squared. And it's given in units of MeV, millions of electron volts. This binding energy is the amount of energy that needs to be put into the nucleus in order to break it apart into free neutrons and protons again. Let's do an example of calculating mass defect and binding energy. We're going to do this for the boron isotope boron 10. Boron 10 has 5 protons, 5 neutrons, and it has 5 electrons. We're going to combine the protons and electrons together as we do our mass calculations, so we'll just use 5 hydrogen masses for this. We'll also use 5 neutron masses. You can see these two listed here. In addition, we're going to need the boron 10 mass, and we can find that on a table of isotopes, which I'm sure you can find on the internet. The mass defect is going to be the difference between the sum of the free particles, masses, and the mass of the boron 10. So we have 5 hydrogen masses plus 5 neutron masses minus a boron 10 mass. The result, we have a mass deficit, delta M, of 0.069513 atomic mass units. Well, the second part of this problem is to find the binding energy. Well, first we're going to convert the mass deficit in atomic mass units to kilograms or million electron volts per c squared, or MeV per c squared. We do this for units of kilograms by using the conversion factor 1.6605 times 10 to the negative 27 kilograms per atomic mass unit. When we multiply the mass deficit by this, we get 1.1543 times 10 to the negative 28 kilograms. Somewhat unwieldy number. If we do this into MeV per c squared, we simply multiply the mass deficit by 931.5 MeV per c squared per atomic mass unit, with the result that the mass deficit is 64.75 MeV per c squared. The binding energy can then be in either joules or MeV. We simply multiply by c squared in both cases. When we do this on the kilogram side, we get joules, 1.0388 times 10 to the negative 11 joules. And if we do this in MeV, we get a very simple result. Since the units we were using were MeV per c squared, we simply cancel out the c squares and get 64.75 eV. I think you can see that working in MeV and MeV per c squared units is far more convenient.